Hi, my name is Jackson Holm, and today I'm going to be talking about synchronized chaos in the Lorenz system and its applications to signal masking. So this is my table of contents, so I'm just going to stay on this slide for just a second in case you want to look through some of the topics I'm going to be talking about, and then I'll move on to the first slide. So our first slide is about chaos in dynamical systems. And the question that I want to answer for those who may not know is what is chaos, or rather, what is a chaotic system? How can we define it? And the answer is a little tricky because there isn't really a universally accepted definition of what a chaotic system is. But for the purpose of this slideshow, we're going to be using Stephen Strogatz's definition from the textbook Nonlinear Dynamics and Chaos. So by that definition, there are effectively three characteristics that a system must satisfy in order to be considered a chaotic system. The first criterion is that it must exhibit aperiodic long-term behavior. And effectively what that means is that for a given initial condition, as time goes to infinity, the solution curve from that initial condition can't settle into any sort of periodic motion. It can't settle into a stable fixed point or a stable limit cycle or any of the different sort of uh, stable periodic orbits that you talk about in dynamical systems. So effectively, it needs to be aperiodic as time goes to infinity. And that characteristic actually doesn't have to apply to all initial conditions within the system. It effectively just needs to apply to enough of them. There's a couple different definitions that get used, either some set of initial conditions in some open set within the plane or three space or whatever. Or sometimes people say that it needs to apply to something with non-zero probability if you were to randomly select an initial condition, something along those lines. Our second characteristic is that the system has to be deterministic. It cannot be non-deterministic. So effectively what that means is that if we have parameters or functions in our system, they cannot be like random or very noisy. The sort of weird kind of chaotic behavior that we want to see in the system needs to arise from the nonlinearities within the actual differential equations rather than just coming from some sort of random or noisy parameter or function. And then our third characteristic, which is the one I want to focus on more because it'll affect more of the things we're talking about in this presentation, is that the system must exhibit sensitive dependence on initial conditions. And so effectively what this means is that in a normal dynamical system, a non-chaotic one, what we might expect is that initial conditions that are very close to one another will have relatively similar solution curves as time goes to infinity. They might settle into the same stable fixed point, or they might settle into the same stable limit cycle, things like that. In a chaotic system, by definition, what we must have is that initial conditions that start very, very close to one another um, exponentially diverge from one another as time goes to infinity. So that leads us into discussing the Lorenz system. So the Lorenz system is a specific system, a specific example of a chaotic dynamical system. So you can see the equations for it here on the slide. It's the x dot, y dot, z dot. As you can see, it's three differential equations in a system. There's some parameters there, sigma, r, and b. And I have some graphs down below. Those are actually just two-dimensional cross sections that I generated in MATLAB of one solution curve of this system. So this equation is chaotic, or this system rather is chaotic. And we know that because there are proofs that validate that it fits those three criteria that we talked about on the last slide. There are a little complicated, and I'm not going to go into them in this presentation just because they'll take some time. But trust me, and you can look it up on your own, the Lorentz system is a chaotic system. So specifically why I want to talk about the Lorentz system is I want to talk about a implementation of the Lorentz system using physical real-world circuitry done by Cuomo, Oppenheim, and Strogatz. And so effectively what this was is a circuit that acted as a transmitter and a circuit that acted as a receiver. And they were built to follow the Lorentz equations. And so you can see here the equations for the two circuits. These were derived, I think from Kirchhoff's laws. And you can see the U, V, and W, the transmitter equations, are effectively just rescalings of the Lorentz equations from the past slide. The receiver equations are effectively the same thing, except you'll notice that instead of relying on U sub R, they rely on U of T, which is actually the U from the transmitter. And so that's why it's the receiver. It effectively gets the U signal from the transmitter and uses that to drive the equations in the receiver circuit. And so what this leads to, and the thing I want to talk about, is synchronization. So effectively, the idea here is that the receiver eventually in its U sub R will generate something very, very close to the U from the transmitter, even if they start at different initial conditions. So to explore this, we're going to look at the error signal. So what this is it's just the D, which as you can see in the last slide is the transmitter, minus R, which is the receiver. So it gives us the difference between the two solutions, basically. And so these equations, E1, E2, E3, are derived from the equations on the last slide. And from those equations, to figure out about synchronization, what we can do is we can actually define a Lyapunov function. And so that's what that E is there, is it is a constructed Lyapunov function that, as you will notice, you can see all the squared terms there. That E is always positive, although it's 0 when the E's equal 0. But that's okay. That's allowed within constructing the Lyapunov functions. And its derivative, E dot, which is right below it, is always negative, again, except for at E1, E2, E3 equals 0. And so effectively what this guarantees is that we have this sort of positive function. It's all above 0, except for at that one point at 0. But it's always a negative derivative. So it's this sort of downward sloping bowl. And so the solution curves in E effectively run down this bowl to 0. And so this function effectively guarantees that as time goes to infinity, the error goes to 0. And that is the definition of synchronization. So effectively what we're saying is that over time, as time goes to infinity, the receiver circuit will be able to very, very closely approximate the signal coming from the transmission, if that makes sense. So what this leads to is a discussion about a technique called chaos masking. And so what chaos masking is it's the idea that if you take that transmitter and if you were to essentially hide a signal underneath the chaotic signal coming from the transmitter, that there would then be, because of this synchronization, a way to subtract off the chaos at the receiver and to get back out the secret message. And so I went ahead, I implemented these systems in MATLAB, and I generated some figures to kind of show you how this works. So this graph here is the error in transmission, that U. So it's UR, which is the signal that the receiver has recreated, minus U, which is the original transmission. And effectively what you can see here is that as time goes on, it kind of hovers around 0. Now it's not exactly 0, obviously we have a little bit of error here and there, but it's pretty close to 0. And so what this results in is our ability to do the following, and that is to recover that hidden message, that hidden signal. So what you're seeing here is U plus M of t minus UR. So what that is the signal, the chaotic signal coming from the transmitter plus the hidden message in it. So this is sort of the sum total signal coming from the transmitter, and then subtracting off the recreation of the chaos that we get from the synchronization at the receiver. So effectively what this should give us is it should give us the unmasked signal if this works. And as you can see from the graph, the solid blue line is that recovered unmasked signal, and the dashed red line is the actual signal. I just used a sine function to do this as the hidden signal essentially. But so what you can see is that they are very close, and certainly if we were like listening to these as audio, uh, it would certainly probably be distinguishable to us. So the last thing that I kind of want to talk about here is unmasking chaotic data, not in the sense of unmasking it at the receiver, but unmasking it as an eavesdropper, essentially. Um, and I just want to briefly talk about it. I don't have time really to necessarily go into the specifics of all of it, but GEDS short and black. There's a 1999 paper. I will have it in the citations at the end. And what they talk about, they have an implementation of a similar system. They're using lasers instead of circuits, but that it's effectively a physical implementation of the Lorentz system. And what they show in their paper is that the assumption that a lot of people had, which is that the the various parameters in this sort of laser system would be very high dimensional, making it very difficult to um, sort of eavesdrop on the data, um, is actually false. They were able to reduce the system down to 4 different parameters, which they, from the laser transmission itself, could estimate and then recover the message without having the receiver. So effectively what that means is they've shown that at least in that physical implementation, there is a problem with the security of the chaotic mask. Now, more promising for the concept of chaotic masking is DeFalco, Mazzone, Cruz, and Fratellocchi's 2019 paper, in which similarly they have a physical implementation of the Lorentz equations, this time using a certain type of microchip. Um, and effectively, they show in their paper that using this certain type of microchip, there is really no way to intercept this data and unmask it, so to speak. So that's a relatively new paper, and it was pretty complicated, and I won't go through it fully, but it'll be in the citations. But essentially, that maybe gives some hope that certain physical implementations of this system may in fact be secure. So here are my references. I will just sort of leave these pages up for a little bit so that you can look at them and access any of these papers that you're interested in learning more about. And then this is the nonlinear dynamics and chaos textbook that I pulled a lot of this information from by Stephen Strogatz, and those are all my references. So I hope you enjoyed this discussion on chaos theory and chaotic masking. Yeah, thank you.